Hi everyone, welcome back to another video. Today we're going to talk about Ferrers diagrams. So the first thing I'm going to do is just like introduce what Ferrers diagrams even are. So um, remember partitions. If you can partition the number five into sets of numbers that add up to it into parts uh, that aren't ordered, then you can create combinations like um, 1, 3, 2. Uh, you can also do uh, like 2, 1, 1, 1, 1, 1, 1, 1, 1, 3, 1, 1, etc. Um, and these are weekly decreasing. So another representation that we can do would be using the Ferris diagram. The Ferris diagram is just replacing each of these parts into like like either blocks or like dots. In this case, if we wanted to represent the partition 5 as only one part, just 5, then we can represent that as 5 blocks. This we can represent by defining that weekly decreasing by having established one row, the top row being the first, and the greatest uh, number of parts in one part, like the greatest length part as the top one. And then as you go down, the next row cannot exceed the length of the previous row. So in this case, we have this as that. 3, 2, we would do the same thing, but have this and so on. And doing this kind of representation lets us see a better picture of partitions, and we can later on use this to describe a recurrence relation to find the partitions uh, of any integer, um, any positive integer, that is. And so for Ferris diagrams, there's also this thing called self-conjugate partitions. And there's also conjugate partitions. And we can express them in this way. So if we had this, the 3, 2 diagram, then we can draw a line between these two. And basically we reflect this over that. And we know that this is an involution because, which means like it can go back and forth because we know that like there's only one way for this to go there, and there's only one way for it to go back, right? Reflections are rigid transformations, so they can be reversed, and therefore we have a bijection between these conjugates, which is why you call it conjugates that they can go back and define each other. So in this case, we would call it U plus U prime. Um, and that's basically saying that the conjugate, which is this, would be equal to this. So this is called a self-conjugate, where the self, like if you reflect it over, you get the same thing. It's self-conjugate. Um, but in this case, if you reflect it over, we get this partition, right? Which is uh which is also another partition. It's the 2, 2, 1. So we had the 3, 2, and we also had the 2, 2, 1. So these two are indeed valid partitions, and so we can see that these two are conjugates. And what we're trying to do here is we're trying to see like how we can use this to define all the partitions of an integer, right? If we are able to establish uh, that a partition is made of only self-conjugates and otherwise only conjugates other than that, then we can create some kind of uh, like formula to help us define the number of partitions. In this case, it is pretty obvious that there's only two possible ways because if we're gonna have any diagram that is not like symmetrical around that line, then we're going to have a conjugate. Otherwise, we have a self-conjugate. Uh, and so that's pretty clear. Um, And so you do know that you should know that the length uh like of like this conjugate or like this um partition will be like actually sorry. The length you can define as like how long this is for that one part. So length of like one part UI would have to be equal to the first row, the number of partitions in the first row, which is equal to you you can name it a different name, but that will be equal to number of rows there. Um, and so that we know the number of rows to be established as n for a partition. Um, I'm sorry, not n, sorry. That's k because you have k parts. And so if you have k parts, then um, then you know that yeah. So this we can say it's k for the first row. Uh, for this only the first one. Um, but if we establish that that's k, then we know like we can use this and split it into two cases. So the first case would be um, I say take this partition uh of nine, right? This is a partition of nine. And so for this partition, if we split it into two cases where you can either have uh, a block at the last row, or you can have two or more blocks at the last row. If you do have only one block, then we can say, oh, let's take out this block. If we do take out that block, we are left with this partition, which is of eight. And what we know about this is we can go back from this to the other one by just adding one block and then like the next row. And you can see like the bijective property of that. Um, and so if if that force is a bijection, then we can write that as P of uh, n minus 1 into k minus 1 parts. And then the next possibility is to have two or more rows. And let's say for two or more rows at the last row, like I meant two or more parts in as the last row, like the length of the last row, the like the length of the sorry, the length of like the last row, which represents like the last part of the partition. If it's greater than two, greater or equal to two, then we can just um like we can just take this out and ignore that these are equal um partitions. But let's just say we have the same. Yeah, okay. So this is also a partition of nine. So for the ones with more than two rows at the end, I mean more than two uh columns or like lengths at the end, then we can take out this entire column, and that's gonna make this partition, and this partition is gonna be a partition of one, two, three, four, five, five, right? So you're basically minusing the number of parts. So for this case, we can also like go back bijectively because you can just add another row behind it, right? Nothing's gonna change. And so we can write that as n minus k because k blocks are being removed, and then you're still doing k parts, right? Because you still have these k amount of parts. And so this is actually a valid formula recurrence relation that we can define partitions. And yeah, that's Ferrers diagram. It's very useful for looking at partitions in a different way. And in this case, we were able to like discover a property of partitions that we weren't able to otherwise with just writing it out. And a different way that you can represent it is just drawing dots. I encourage you to try to like find all the possible Ferrers diagram for any integer. It's the same thing as finding number of partitions or like all the partitions for a number using sets. But this is just another fun way to do it. Yeah. Hope you have a nice day.